Hello everyone, welcome back. This is the Signal and the Noise podcast, episode 2. In this episode we'll be discussing infinite context, or how you can use a large language model to build a second brain. We'll move away from the search engine mindset and into a reasoning engineering mindset. We'll discuss the Goldfish Genius. Why does the LLM know everything about the world and nothing about you? We'll then move on to the semantic filing cabinet. How to consistently and constantly remind the model who you are. And then we'll finish with grounding the ghost. So managing truth, citation, and hallucinations. The introduction. The model is not the whole system. Reliability emerges from system design, not from model size. There's an ongoing discussion in the large language model community at the moment over scaling versus system design or engineering. And we seem to think that we're coming up to the limit of gains from scaling. So we're moving away from a system where a paradigm where we need to build a bigger model, but we now need to build a better system of using the model. You can break down the system into 3 chunks, 3 sections. So we have the brain, the memory, and the ethics. We've sort of referred to those through this presentation as the Goldfish Genius, the semantic filing cabinet, and grounding the ghost. So the brain knows everything but needs context. The memory, the semantic filing cabinet, provides these consistent memories. And then the ethics constrains reasoning and provides trust. If you remove one of these components, then the whole system falls apart. So part 1, the Goldfish Genius. Despite having been trained on the entirety of the internet, the LLM does not know you. When you close a chat, the memory of that conversation is gone. This is the goldfish effect that frustrates so many people who use LLMs. Modern LLM systems, we now see them starting to get around that. They have their own memory systems, but if you want to implement and build your own system at an enterprise level, then you have to be aware that it's not just enough to have a large language model. You need to have the rest of the system designed and engineered to work with it and attach to it. Vast intelligence is not the same as infinite recollection. Normally, once the conversation is over, all memory of it disappears unless it's deliberately added. Understanding this limitation is the foundation of everything that follows throughout the rest of this course. We need to think of it like a goldfish genius. It knows everything about the world, but it can only think about what's written right in front of it. And once it's finished, it wipes the blackboard clean and forgets everything that it's just wrote down. Intelligence without memory feels broken to humans. The model has read every word you've written, but it has no memory of you. It has no memory of your goals, your preferences, your project history, any previous decisions you've made, or any emotional or strategic content that you require. We must provide continuity, resupplied constantly. Continuity must be resupplied, not assumed, and that leads us on to the model's context. So the context is its window of attention. We discussed attention in episode 1. This is what is aware of right now. It's finite and it's continuously updating. And then the model's scope is limited to the current conversation. Sorry, the context scope is limited to the current conversation. It's not just a token limit, it's a sliding door of attention. Anything outside the context does not exist for the model. Let's illustrate this here. Our red boxes refer to the context. Our model can see the red boxes. The white boxes exist, but they're not seen by the model in this instance. How do we solve this? The naive solution is to copy and paste everything into the chat window. This is long, confusing, and often contradictory prompts, long chains, discussions, changes of opinion, and this leads to wrong answers. We learned that models tend to gravitate towards the median answer rather than necessarily the correct one. And flooding the context window with everything at the same time removes the benefit of ever having a context window in the first place. We can definitely do better. Our failure modes for the naive solution include attention dilution, contradiction weighting, recency bias, and median answer collapse. Again, if you add everything to your context, nothing's in your context, or there's nothing special about your context. The contradictions are there. You have your recency bias, the last thing you talked about, and then, your median answer collapse. You'll collapse to the mean, you'll collapse to the center, you'll collapse to the safe, uninspired, uninteresting answers. This leads us on to part 2, the semantic filing cabinet. Traditional computers store information using exact keys and look for keyword similarity. Retrieval is literal and brittle. Dog does not equal canine. Car does not equal automobile. Only the surface level analysis of language is conducted. If you want to use synonyms, good luck, they must be directly encoded. And this can be thought of as a what is it called way of thinking. LLMs use a semantic search to measure the distance between ideas, not necessarily the overlap between words. Words are not stored as labels, but as locations in something that we might refer to as meaning space. This is our solution space. This is the separation between tokens. However you like to think about it, a nice general way of thinking about it is meaning space. Retrieval becomes find me texts that are near this idea, with something like dog being close to canine, puppy, and pet. Semantic searching is like asking an expert what's relevant. And these locations, as we mentioned before, are called embeddings. The embeddings don't store the text, they store the relationship between the meaning. So I've tried to map out a slightly more interesting meaning space here. So we have two objects, key objects, cat and dog. They're both quite close to pet. They're both quite close, similarly close to animal, although animal's a little bit further away, because semantically cats and dogs are often pets as well as always being animals. And feline and kitten are also very close to cat. Canine and puppy are very close to dog, but canine and puppy are not particularly close to cat, although they're closer to animal and pet than they are to cat. The same is true of feline and kitten. A human doesn't need the same wording. We understand the intent. This matters because it allows LLMs to match paraphrases, apply cross-domain reasoning, be robust to phrasing differences, and recall information without the need for a manual synonym list. LLMs, or semantic reasoning, feels more human, and it's also more forgiving. So in a practical way, you might ask the question, how do I stop my app from crashing when it runs out of memory? So there are things here, for example, memory, which occur in the solutions on the right hand side, but there are also things like heap allocation, garbage collector, which don't appear directly in the input text, and then something like OOM killer, for sure that's not there. But because we're looking at things from a semantic point of view rather than a keyword point of view, rather how is this spelled versus what is this like, we can start to sort of pick out sections of our training data which are not directly referred to in the input, but are absolutely useful to know about in the output. So I'm going to introduce a concept called a vector database, or the actual semantic filing cabinet. So vector databases are storage devices optimized to search for embeddings. So this isn't the same as a traditional database where you might have a traditional SQL type query where select all where title equals dog. You're now searching for meaning rather than keyword, so that your search term becomes something like find everything about dogs. You can see from our previous slides that things about dogs might not necessarily have the word dog in them. They might have things like canine. This new way of thinking about querying databases will pick up these differences semantically rather than directly. These vector databases are a powerful gateway to persistent memory. They'll contain, depending on the implementation, institutional knowledge, domain expertise, standard operating procedures, best practice, specific guidance, and any personalization. This can turn your chatbot into an assistant very, very quickly if it's connected and engineered well. So how do we build a semantic filing cabinet? We can chunk our data to make it more efficient. So this is taking a large document and breaking it down into chunks of text, smaller subsets of the document. We might follow a process that's something that looks like this. So we'll break the document down into chunks. The chunks will be converted into embeddings, and then the embeddings will be stored on the vector database. From then we can embed the user query, and then we can retrieve the most relevant chunks from the database. Those chunks can be then injected into the prompt as context, and then we can send this to a large language model in the same way that you would send the prompt. This will be executed as a large language model as usual, and now the response is grounded in the specific and consistent context, not just generic large language model training data. A quick note on document chunk best practices. Start chunking by existing structure, headings, sections, paragraphs, and so on. Chunk tables and code together, something like 200 to 400 tokens per chunk, with technical writing being a little bit shorter and maybe narrative writing being a little bit longer. It's also important to overlap your chunks so that key information isn't split across boundaries. So something like 10 to 20% of your previous chunk should be included in your next chunk. So maybe 30 to 80 tokens depending on your documents themselves. Keep one topic per chunk and avoid the junk in the document, so headers, footers, comments, and so on, unless they're relevant. So semantic retrieval matters in practice. The responses are now specific, they're not general. Responses are now repeatable, they're grounded within the information you want it to have, and they're also scalable beyond the prompt limit. The system is now reliable and explainable, it's traceable, and this approach underpins tools like AI assistants, enterprise search, private chatbots, and agentic workflow. The language model itself is still a Goldfish Genius, but we've built a way to help it remember the important things. So your user prompt now hits the vector database, which creates an augmented prompt. The augmented prompt then feeds into the large language model. The large language model has contextually relevant responses, whereas if you just go from the user prompt straight into the large language model following the red trace, the output is just a generic response. The context is rebuilt dynamically from memory rather than persisting on its own. So we need to engineer this to reliably give our large language model the information it needs every time we ask it a prompt.
Okay, let's move on to part 3, grounding the ghost. How can we tell if the output is true and where it comes from? For this, we need citations, truthfulness, and hallucination control. This really is an issue of the ghost of the gaps. Models appear knowledgeable, confident, and fluent, but in reality, they don't know what's true, they don't know when they're wrong, and they're really just being predictive. A ghost is intangible, persuasive, and ungrounded, and we aim to fix all of that. Firstly, what is a hallucination really? Many people talk about hallucinations when discussing large language models, but it's important to have a clear and specific definition. A hallucination is a plausible and coherent response that is completely wrong. It's the model doing exactly what it was trained to do, which is predict the next token. It doesn't know what's right, it doesn't know why anything happens, and they can happen when the model has insufficient context, the question exceeds available knowledge, or the model is forced to answer anyway. If guessing sounds right, it will guess. It's a helpful assistant after all. So we can look at these as a taxonomy of types. These can be forced completeness, ambiguous queries, conflicting context, overgeneralization, or missing information. We must always remember that fluency is not the same as truth. If you ask a model about a policy that is not in the policy document, it will not say, "I do not know." It'll make up a plausible policy. And this is due to some of the following issues: missing or incomplete context, broad questioning, ambiguous prompts, domain-specific knowledge gaps, and pressure to respond in what it considers a helpful way. Grounding is the antidote to hallucinations. It's constraining the model's output to known sources, retrievable documents, verifiable facts, and the model changes from creative synthesis to contextual reasoning. From a conceptual point of view, this means we go from answer this question to answer this question using only this information. Retrieval is necessary, but it's not sufficient. Retrieval and embedding can create relevant context, but it doesn't guarantee correct usage, faithful summarization, no hallucinations. So we must also control how the model uses the retrieved data, what it is allowed to say, and we must always remember that it still works probabilistically and not deterministically. Grounding reduces the risk, but it does not eliminate it completely. Prompts encourage grounded behavior, but they do not enforce it. Large language models are trained to be helpful, so asking the model to suppress behavior that it was trained to do. It may not always follow your instructions, especially if the question feels obvious, the model has some strong prior knowledge, or that the context is almost sufficient. So, what steps are necessary for effective grounding? We need to consider retrieval quality, context delimitation or knowledge boundary enforcement, answer format enforcement, and also, often most importantly, post-generation validation. So after the text has been generated by the model, something else needs to validate it. Let's look at these in a little bit more detail. Retrieval quality. If the truth is not retrieved, then no grounding will help. The grounding often fails because the right chunk wasn't retrieved, or the chunk was too small, or that the relevant information was split across chunks. We discussed the best practices for data chunking already, so follow them. Context delimitation. You should clearly mark what counts as allowed knowledge. For example, you may only use the information inside the following context, and then specify the context. Anything outside this block must be ignored. Here you're giving the model the positive instruction and also the negative instruction, so you should counterbalance both sides of the discussion. This level of specificity works much better than vague wording. Answer format enforcement. Instead of just asking for a citation, require a structure. Here we outline a potential structure. For each claim, use the following structure: claim, and then write the claim, evidence, quoted directly from the context, and the source ID. So we can go back and check the source ID to make sure it does contain the evidence that is quoted. Structured outputs dramatically improve grounding confidence. The answer may be verified by a second model. We can then structure a new prompt with a forced output mode saying, is this answer, then specify the answer, fully supported by the context, then supply the context, and then we give it the structure, the claim, whether or not it's supported, and then some assessment of the probability of it being supported, maybe between 0 and 1. This gives us both the output we're looking for and a potential threshold metric that we can use later. You may programmatically then send claims with less than a threshold probability for a manual review if you decide that that wants to be part of your workflow. As we move from simple prompting to reason engine creation, it's worth remembering this. Grounding is not a prompt, it's a pipeline. Prompts ask for grounding, but the systems we build enforce it. After all, the model is not the product, the system is the product. This is an overview of a simple potential design. The user queries, the retrieval picks up the context from the database. This is then passed to a context assembler, which sends it to the large language model. The large language model then creates its response, and the response is reviewed. In a more thorough and full way, this might look something like this for a sales assistant large language model system. A user may ask, can I get my money back if I bought a digital product last month and already downloaded it? A plain text request that a large language model can handle. We then supply the rules. Only use the provided context. If the answer is not fully supported by the context, say I don't know. Here we're giving it its fail case. Cite sources for every factual claim. Do not use external or general knowledge. Then we provide two documents here for clarity and simplicity, the policy refunds document and the policy shipping document. The context assembler then looks at the two documents that it has access to, determines that source A, the policy refunds document, has the correct information in it, and then it uses that to build its response. The response then comes out as no, digital downloads are not refundable once accessed. This applies even if the purchase was made. This applies even if the purchase was made within the 30-day refund window, citing source A, which we can see from our reference table is the policy refunds document. This is a good response to a user query. Every claim is supported by the retrieved text. Its citation points to the exact chunk for reference. No external assumptions have been made, and no extra information, for example, the shipping document, is included within the output. It's confident, but it's constrained. So grounded answer is one where every claim can be traced directly to retrieved context, or the model explicitly declines to answer. Here's a bad example of systems engineering, a direct link from the input prompt to the output response. Again, can I get my money back if I bought a digital product last month and already downloaded it? The response being, digital products are usually non-refundable under consumer protection laws, although some companies make exceptions. This is a bad response to the user query. It uses external knowledge. It doesn't give us any citation. It sounds plausible, but is unverifiable. And because it's using general knowledge rather than specific company-related knowledge, it's not useful for the end user. Citations make the model's reasoning inspectable and verifiable. Verifiable means that the user can check the claim. Traceable means the user can check where it came from. And discipline, the model stays anchored in the context. Because even approximate citations are vastly better than no citations whatsoever. Grounding gives the user trust in the model. We go from users must believe the model to users can verify the answer. We go from errors are subtle and dangerous to errors are localized and obvious. And we go from confidence is misleading to trust becomes justified. Smart but risky becomes reliable and bounded. And importantly, it becomes automatable. The three layers then work together for production-grade large language model products: the brain, the memory, and the ethics. The Goldfish Genius that knows everything but needs context. The semantic filing cabinet that provides consistent memories. And grounding the ghost constrains reasoning and provides trust. Remove one of these components and the whole system falls apart. What grounding does not do. Grounding does a great job at reducing hallucinations, managing uncertainty, and making systems auditable. This can lead to safer deployment. However, it is not a complete failsafe. It will not make the model omniscient, it will not eliminate all errors, and it will not replace human judgment. The future of AI is not just bigger models, it is better grounding, retrieval, and constraints.